All right, so in the last module, we learned how to compute integrals using logarithms, exponentials, and inverse trig functions. We learned about inverse functions so that we could talk about inverse trig functions and logs and exponentials. In this section, we're going to be doing something altogether different. We're going to be looking at how to find the volume of different particular solids that are created either by slicing something or by volumes of revolution. So we're going to determine the volume of a solid by integrating a cross-sectional area. That's the slicing method. We're going to find the volume of a solid of revolution using the disk method, and find the volume of a solid of a revolution with a cavity using the washer method. So these are the things that we are going to be doing. Okay. So let's just talk about the fact that if I have, where's my little notebook? My little notebook. Okay, I feel crazy. My little notebook disappeared. All right, I'll have to use something else. I'll have to use stack gum. Okay, so here is a piece of gum. All right, and let's just, it's thin. So basically has no volume, although it technically does because it's gum, but it was a gum wrapper. It has, so we can look at the area of it. It's actually rectangular, mostly rectangular. But if I then start to stack a bunch of slices of gum next to each other and stack them like this. So now I have something that has volume. Okay, so one of them is just a thin area. But when you stack them alongside of each other like this, you end up with volume. So that is what we are doing today. We are taking something like one slice of bread. Once we find the area of that slice of bread, we can stack a whole lot of slices of bread, and then we have a loaf. And we can find the volume of the loaf by summing up all the areas across the section. The only thing is, we're not going to be doing a finite sum of areas. We're going to be doing an infinite sum of areas, and that gives us an integral. So here we go. Okay, so our formula that we are going to be using is that volume is going to be the integral of the area. Okay, the integral of an area dx. So we need to figure out what that area is. So the first thing I want to do is volume by slicing. All righty. So let's suppose I have a region on the ground. So let's say I'm going to have some region here. Okay. So this is my region. This is a function. Y is equal to f of x. And I'm at A to B. All right. Now, if I take cross-sectional areas, let's say these are rectangles, and I take rectangles and I stand them up along the whole region, And I keep taking rectangles all the way through. As you can see, I can find the area of any one of these particular rectangles. So here's the rectangle. I need to find its area A of X. So its area well, it's a rectangle, so it's going to be its base times its height. Well, I already know just from how this picture is drawn what its base is. I don't know where E4 came from. Gotta go. Okay. So let's draw a different picture in the XY plane. All right, so here's A from some A to some B. Uh-oh. And then here is the function Y. So this is Y is equal to F of X. And as you can see, I have this rectangle. Which is standing up in the air. And then there's another rectangle. This one might be bigger. So these rectangles are standing up in the air. These are the same area rectangles right here. So where's the base of the rectangle? So here's the base. The base is this distance, but for that X, this distance is just Y of X. For this X, it's Y of X. So we can see that the base of the rectangle has length Y of X, and then we just need to figure out what the height is. Okay. So for each slice, the cross sections are rectangles. So the cross-sectional area is just the area of a rectangle. Okay, so that is A of X. So once we find A of X from this particular problem, which is length times height, and for us the base or base times height, I should have written length times height. For us here, the length is the bottom. We know the length is Y of X because that's what's laying on the ground. Okay. All right, so here is the technique for trying to solve a volume by slicing. The first thing you have to do is draw what you're looking at. Okay, so draw the loaf of bread, draw whatever it is that you're trying to find. Okay, so just draw it. Then the second thing is identify the limits of integration. Where do the slices start and where do they end? So right here, struggling today. Okay, so notice this is my solid, is some strange thing, a loaf of bread, okay? And it starts at x equals a and ends at x equals b. Those are my limits of integration. Then I need to determine what the cross-sectional areas are. Are the cross-sectional areas slices of bread? Are they triangles? Are they circles? Are they semicircles? Are they squares? They could be anything, but the problem's going to tell you. Then you need to find the formula for the cross-sectional area. That's A of X. And after you find the formula for the cross-sectional area, you're going to substitute that into the integral. And of course, number 6. Oh, go back. You're going to compute the resulting integral. Okay. All right, so let's do this. Now, I did realize in my last class that I should have done example 2 before I did example 1. So I'm going to do example 2 before I do example 1 because example 2 is easier and example 1 is harder. So let's do example 2 first. And we're going to rename it example 1. Yikes. Okay, so the base of a solid, that means the bottom of this solid, is bounded by the curve y is equal to square root of x and the line x equals 4. The cross section's perpendicular. So we have a base. Here's the base. The cross sections are slices that go like this. And if you add these slices up or stack them up, you're going to end up with a solid. Okay, so the cross sections perpendicular to the x-axis are squares. Find the volume of the solid. So let's draw this. So first off, let's draw the base. All right, so here's the base. It says the base of the solid is bounded by the curve y is equal to the square root of x. That looks like that. And the line y is equal x to the 4th. X is equal to 4, I apologize. So here's our base. So imagine that this is a paperweight and the base of the paperweight is in this shape. But the structure of the paperweight are squares. So that means that I have squares sticking up in the air. So this square is sticking up in the air. Here's another one. This square is going to be much bigger. Whoa, not that way. That square is sticking up in the air. Then over here, there's a little tiny square sticking up in the air. Okay, so these squares are sticking up in the air like this. All right. So for any given X, here is the square at that X that's sticking up in the air. All right, if I were to draw this three-dimensionally, yeah. And here is y is equal to the square root of x. Oh, come on. This is y is equal to the square root of x. And here is the line x equals 4. Okay, so here's the base again. And so now this one has squares that are sticking up in the air. Good, that's a perfect, that one's good. Then I maybe have a bigger square. Okay, so the squares are sticking up in the air, and these are the cross-sectional areas. So at any x between 0 and 4, there's a square. Okay, so we've drawn it. So that's the drawing.
I have a question.
Yes.
Why is the 4 there? Since it's a positive 4, why does it look like it's a negative 4?
I'm trying to think why it looks like a negative 4 to you as well. Do you
Because
see?
in that part of the graph, there would be a negative x value and negative y values.
Okay, you talking about this picture.
Yeah.
Okay, because in this picture, it's drawn crazy. In this picture, this is the y-axis, and this is the x-axis. So this picture is turned. So,
Okay.
yeah. And so in order for me to be able to draw it so that the cross-sectional areas are sticking up in the air, I got to tilt the y-axis on the ground. I got to make the xy be on the ground because that's the base.
Okay, thank you.
Okay, back here is negative x. This is negative x back here, and this is negative y over there. Okay.
Thank you.
You're welcome. That was a very, very good question. Okay, so identified it. So the limits of integration. Well, the squares are going to start at x equals 0, and they're going to end at x equals 4. So therefore, the integral, the volume is going to be the integral from 0 to 4 of a of x dx. So that's the first thing. Then next, we have to identify the cross-sectional area. Well, the cross sections are, the cross sections are squares. Okay, so for given a square, its area is the length squared. Okay, whatever the length is, the length squared is the area. So let's go back to our picture. So given an X, here's the length of the base of the square. Here's the length of the base of the square. So for a given X, that is this height, and that height is Y. And in this problem, it is the square root of X. So my squares look like this. Where the bottom is the square root of X. So this side has to be the square root of X. So it's because it's a square. So now I know that A of X is the square root of X times the square root of X. But that's just X. So then 6, the volume is the integral from 0 to 4 of A of X dx. But that's the integral from 0 to 4 of X dx. Okay. And that turns out to be 8. Okay, any questions about that? The next one's more difficult.
How'd we get 8?
We got 1/2 X squared, which is 1/2 of 4 squared.
Okay.
One half 16 minus 0, 8. Is that clear?
Yeah.
Okay. All right. Okay. Next problem. I'll give you a minute to copy it down. Okay.
Hello.
Yes.
Quick question. Let me see. After the ax dx equals 0 to 4 x, how's that? What did you do to get that x right there?
This X,
Yeah. Or
that
is it?
X is the area. The area was the square root of X times the square root of X, which was X. So the original was the volume is the integral from A to B of whatever the area is. So I had to find the area.
So that would be x1/2 times x1/2,
Yes.
and then that would get x to the 1/4.
No, you add the exponents, not multiply.
Oh, you add the exponents, so it'd be 1.
And the square root of something squared is just that thing. So the square root of X squared is just going to give you X.
Okay, so that got 1, and then when it got to the 1/2, is that from?
That's from X to the N plus 1 divided by N plus 1. The power rule for integration. No.
Oh, okay. All right. I see it now.
Okay,
Thank you.
you're welcome. Okay, any questions? Wow, I think how sick I was the first couple days of class when I was teaching, how awful I felt. Wow, I feel so much better now. My God, it was terrible. Okay. Here's the next problem. All right, consider the solid whose base is bounded by the upper semicircle x squared plus y squared equals 4, and whose cross-sectional areas are equilateral triangles. Find the volume of the solid. Okay, so let's look at the base. So the base is the upper semicircle x squared plus y squared equals 4. Now, here's my base. Okay, so that's my base. It's the upper semicircle. All right, I can write that as x squared plus y squared is equal to 4. Or if I want to write it as a function, y is equal to the square root of 4 minus x squared. So that is this curve. Okay, so that's the base of my paperweight. So if I pick my paperweight up and looked at the bottom of it, I would see a semicircle. Put it back down on the ground, and the things sticking up out of it, the cross-sectional areas are squares. So I'm going to get something that looks like this. No, they're not. The cross-sectional areas are equilateral triangles. It's kind of hard for me to draw an equilateral triangle like that, so I'm going to do my best. So here I would have this. And then on this side, I would have that. And then on this side, I would have the same thing. And I think that's a pretty darn good equilateral triangle. So my areas sticking up in the air look like this. They're equilateral triangles. Okay. If you want the 3D version, I'll try my best. Whoa, I need that. Okay. Yeah. All right. So here, as you can see, this is the curve y is equal to the square root of 4 minus x squared. And then sticking out of it are cross-sectional, out this cross-sectional area are triangles. Come on. There you go, cross-sectional triangles. So our equilateral triangle. All right, so the first thing is, what are our limits of integration? And that is, where do the triangles start and where do they end? Okay, well, obviously the triangles start way over here. I can't even draw a triangle that small. I'm gonna try. The triangles start way over here. Like that. And then they go up to there and then they end up way over here. So the triangles start at this value of X and they end at this value of X. How do I find those values of X's? I have to use my curve. How do I find those values of X's? Anybody there? This is actually the easy part of the problem. Okay, since they lie on the y-axis, this is where y is equal to 0. So you just get x squared plus 0 squared, or x squared is equal to 4. So when y is equal to 0, you get x squared is equal to 4. So x is equal to positive and negative 2. So I start at x equals minus 2 and I go to x equals positive 2. So those are my limits of integration. So I know my volume is going to be the integral from 0. Whoa, it's not. From negative 2 to 2 of whatever area that I come up with dx. Okay, 3. Cross-sectional areas I already know are equilateral triangles. So therefore, I need to find the area of that. So I need the area of an equilateral triangle. Okay. There we go. So what's the area of any triangle?
One half
Is it
base
one
into
half
height.
base times height?
Good. Okay, so the area of any triangle is 1/2 base times height, right? Okay, so we have this triangle and it's an equilateral triangle. So we need to find H. Because the base we actually know. The reason why we know the base is because the base lies right there, perpendicular to the x-axis. And the base is that height. And that height for any x is the square root of 4 minus x squared. That height for any x is the square root of 4 minus x squared. So we already know what the base is. So now we need to find H. Okay, so this side right here is 1/2 B, and this side is B. And the reason why we know that side is B is because they're equilateral triangle, so all the sides are the same. And this is H. So let's use the Pythagorean theorem because this is a right triangle. I know that 1/2 of B squared plus H squared has to equal B squared. So 1/4 B squared plus H squared has to equal B squared. So B squared is 3/4 H squared. So that says B is the square root of 3/2. No, it does not. It says H is the square root of 3/B. That is wrong. This is H squared is equal to B squared. Good. Okay, now it's right. All right, so H squared is the square root of 3/4 times B squared. So therefore, H is the square root of 3/2B. Okay, so now we can find the area. We know what B is. B is the square root of 4 minus x squared. Oh, I can't write that like that. That's the square root of 3/2 square root of 4 minus x squared. Okay, so now the area then of the triangle is 1/2 base. The base is B, and the height is the square root of 3. Oh, I want to write out what the B is. It is the square root of 4 minus x squared. And then the height is the square root of 3/2, the square root of 4 minus x squared. So how nice is that? The square roots multiply and give me the square root of 3/4 times 4 minus x squared. So we have found the area. Yay. That is what we needed. We needed the A of H. So in the previous problem, A of H was just a simple square. In this problem, A of H is a little bit more difficult. A of H is the area of the equilateral triangle. Okay, so the last part of the problem says put A of H in and compute. So I get the volume is the integral from -2 to 2 of A of H, which is the root of 3/4 times 4 minus x squared dx. And that becomes the root of 3/4 of 4x minus 1/3 x cubed, evaluated between -2 and 2. And I get 8 the root of 3/3. Okay, so that's the answer. All right, any questions? These are going to take a minute. So you guys, for those of you who like microwave math, it's not going to happen. These are going to take time for you to read the question a couple times, process what's the cross-sectional area, try to get a sketch on the paper so you can figure out the formula for the cross-sectional area and then be able to integrate. It is not a microwave math problem. This is going to take some thinking. Okay, any questions?
Wait, I have a question.
Okay,
Why is it? Well, we have 1/4 base squared plus h squared equals base squared.
we have,
Like, When we were finding h,
Oh, here.
yeah.
Okay, so we use this. We use a squared, whoa. ABC. We use a squared plus b squared equals c squared. We use the Pythagorean theorem.
I know that. I was saying that we have b squared twice, like written.
You mean here?
Like when we put 1/4 b squared plus h squared equals b squared.
Okay. Did you understand that step?
Yeah, you squared one half.
Okay. Then you subtract 1/4 b squared from b squared. And that's 3/4 b squared.
Okay, okay.
Make that look more like h. Okay. All right, Rodney, is that okay?
Yeah.
Mhm. Okay. Anybody else?
I have a question.
Yes.
What did you multiply to get 1/3 x cubed?
I integrated. I found the
Okay.
antiderivative of x squared.
Oh, I see.
Okay, any questions? All of these are excellent questions. If you have questions, get them out now. We get ready to switch up and do something completely different. Okay.
Okay, I see, Dr. Lott. So that b squared, if you subtract both sides by 1/4 b squared, it's that whole b squared minus 1/4 b squared. That's where you get that 3/4 b
That's
squared.
exactly right.
Thank you.
That's correct. Okay. Next, I want to do volume by dis. So I'm going to have the same formula again. Get the same formula back. Volume is still the integral from a to b of a of x dx. But this time, my cross-sectional areas are always dis. So a of x is the area of a disk. And what is that? What's the area of a disk?
Pi,
Pi what?
pi squared.
Pi r squared.
Yeah.
Okay. So the area of a disk is always pi r squared. So what we have to do is we have to identify the radius. Once you get the radius, then you know what a of x is, find your limits of integration, do your integral, and you're done. Okay. So we're going to revolve about the x-axis a region to make a solid. Okay, so we have something that looks like this. So here's my y is equal to f of x. And I want to take, and I want to look between x equals a. No, look like no a. And between x equals b. And I want to revolve this thing. So what I'm doing is I'm taking a region that is flat. So it could be whatever shape this is. This is a rectangle. And I'm going to sweep it out and revolve it about an axis. And when I come up to the other side, I have a hole. So I have something that is completely solid because I swept out the whole region over an axis. Okay. So let's do it. All right, so here is my region. I'm going to choose an X between A and B. And I'm going to revolve the region. That didn't make it all the way down. And when I do that, okay. Forgot I told you to do that. Thank you very much. When I do that, I get a disk. So here is my cross-sectional area. It is a disk. So my cross-sectional area is a disk. And I need to find the radius of it. Well, the radius is that length. So if I look over here, the radius is this length. But for a given X, that height is just Y of X. So this height is Y of X. So we have to figure out whatever the radius is for our problem. And then when we figure out our radius, we get V is the integral from A to B of pi times whatever radius we have that we find squared dx. And this is the volume of revolution about the x-axis of a region bounded by y equals r of x on the interval AB. Okay, so let's try to do that. So I'll go back, give you a minute to get all that down. And while you're getting all that down, I will take roll. Okay, so we want to take the region between the curve y equals square root of x between x equals 0 and x equals 4 and the x-axis and revolve it about the x-axis to generate a solid. Find the volume of the solid. Okay, so let's draw the picture. Can't find what I want. Here we go. This is it. Okay. Y equals x squared. We know it looks like this. And between this is y is equal to x squared. Oh, y equals square root of x is what I want. Sorry. Okay, so y is equal to the square root of x. And then here is between x equals 0 and x equals 4. So this region is revolved around the x-axis. So here's my region. All right, notice I have this region and it's going to revolve around the x-axis. So when it revolves around the x-axis, it looks like this. Okay, and it's three-dimensional. For any value of x right here, I found this value and I revolved that point about the axis. And there is my disk. So now you can see that the disk starts at x equals 0 over here, because the smallest disk would be over here where x is close to 0. And then the biggest disk would be back over here. Okay. So number 2, the limits of integration. We already said that little yellow disk starts at x equals 0 and goes to x equals 4. So therefore, I know my volume is going to be the integral between 0 and 4 of whatever I find for my a of x dx, which I already know is the integral between 0 and 4 of pi times whatever radius I get squared dx. Okay, looks good to me. Now I need to find the radius of this thing. So I come over here and I drop it like this so I can find the radius. So the radius is that height. Well, that height is y of x, which is the square root of x. All right, so now I already know my cross sections are this. So my area is just pi times r of x squared. So in this problem, my radius is just the height y. So r of x is just y, which is the square root of x. So 5, I get that the area is pi times r of x, which is the square root of x squared. So I just get pi x. So that's my area. That's my pi r squared. So my volume is the integral from a to b of pi times the radius squared dx. But that's the integral from 0 to 4 of pi. My radius squared is x dx. So this is 1/2 pi x squared. Evaluate between 0 and 4. Can you hold on for 1 second? Okay, so this answer turns out to be 8 pi. Okay, I have one more problem I want to do today. I'm gonna give you, whoop, that's the wrong thing. I want to go to module 2. Back here. Okay, so that by far is the easiest problem that you can solve. All right, so this one gets a little bit more involved because I'm going about a different line. So this one's going to require me to find the radius. Okay. All right, so it says the volume of the solid generated by revolving the region bounded by the y equals the square root of x and the lines x equals 1, x equals 4 about the line y equals 1. Okay, it sounds like a whole lot. Okay, but you just have to break it down to something reasonable. So let's draw it. Okay, line y equals square root of x. So let's draw that again. Okay, between x equals 1, so it's bounded by the line x equals 1. X equals 4. And the line y is equal to 1. Okay, so that's this region right here. Here's my region. Okay, so it is this piece. This is the region. So this is the line, y is equal to the square root of x. This is x equals 1. This is x equals 4. And so now, can somebody tell me the limits of integration? I think that should be easy to see.
1
Limits
to
of
4.
integration 1 to 4.
Okay, awesome. Okay, next thing. Okay. So the next thing is for any x in between, I'm going to grab, so I need to take, and I'm going to rotate this thing about that line. So for any x I'm going to draw where I've rotated it. And you can now see my region. Okay, so now we need to find the radius. Okay, so first off, we already know our cross sections are discs. That doesn't change for these problems. Okay, so we need to find the area of the disc, and that means we need to find the radius. So let me get rid of R because that looks like it could be radius and I don't want it to be. Okay, so we need to find this radius, and the radius is here. Here's the radius. So we need this height. Okay, so in order to find that height, we have to take this height, which goes from here all the way down to there, and subtract this part. Then that will give me this part. Okay, so the long line, the distance is the square root of X. And then from here to here is 1. So the radius is the square root of X minus 1. Okay. I'll do it again. We only need the radius, which is just the little green bracket. You have to take this whole height, which is the square root of X, and then you have to subtract off the parts you don't need, which is 1, and then that leaves only the piece that I want. Okay. So now I know R. So therefore, my area is pi times whatever radius I find squared. So now if I plug it in, I get pi, and my radius is the square root of X. Whoa, now how did I wrote a 5? I don't know. It's the square root of X minus 1 quantity squared. So that's my radius squared. So therefore my volume, the integral, we got 1 minute, from 0, so nope, from 1 to 4 of pi times the square root of X minus 1 squared dx. And that integral turns out to be 7 pi over 6. Okay. All right, guys, I would hang on. I'll be back in 15 minutes for office hours. Okay. You guys be blessed. I see you either in 15 minutes or next on Wednesday.
All right, have a good day.
Okay, you too.
Have a good one, Dr. Locke.
All right, take care.